I mean, I'm as ready as I can be. Yeah. Okay. Yes. And should I stay here? Or should I sit down?
Yeah, you can sit down. I think that's
Okay.
more like Kunglika.
Yeah.
Kunglika.
Yeah.
Okay, got it.
Fantastic.
Okay. Ladies and gentlemen, good morning. I would like to welcome you to the second day of our Nobel Symposium.
Yes. And should I stay here? Or should I sit down?
Yeah, you can sit down. I think that's
Okay.
more like Kunglika.
Yeah.
Kunglika.
Yeah.
Okay, got it.
Fantastic.
Okay. Ladies and gentlemen, good morning. I would like to welcome you I can still exercise a little bit. Kunglika, Techniska.
No.
Okay, good morning, ladies and gentlemen. I'm very happy to welcome you to the second day of the Nobel Symposium. And this morning we start with a very eminent physicist from the KTH in Stockholm. And KTH stands for Kungliga Tekniska Högskola, which means the Kingly Technical High School. So Professor Erik Aurell is going to give the first talk, and he has many collaborations, and therefore he also speaks many languages. Among them is Italian and French, and a little bit of German, and maybe a little bit of Finnish.
Yeah.
Okay, little bit of Finnish. Okay, so I'm very much looking forward. But before we start, I give over for a more precise introduction to Professor Yin-Che Ma. Thank you.
Okay, good morning, everyone. And it's my great pleasure to introduce you, Professor Erik Aurell. And so Thomas just say a little bit different language, maybe some little bit Chinese. Ni hao. Ni hao, yeah. So Erik and I are friends for 14 years. We met 2008 in Beijing, China. So from then we start to keep on contact, and it's wonderful to see that this long-term friendship come into a wonderful event like we're doing now. So he is a professor of theoretical biological physics at the Royal Institute of Technology in Stockholm. He started his scientific career as a mathematical physicist. He received his PhD at the Göteborg University in Sweden in 1989 and did a postdoc in between 1989 to 1990 at the Observatory de Nice, France. You were an astronomer. Somehow.
I can tell you when it's fine.
Okay, so and he holds the chair of the theoretical biological physics at ETH since 2003. So he will talk about today fluctuation relations. Thank you.
Thank you. Yeah. Thank you, Yinzi. Thank you, Thomas. Thanks, everybody, for the fantastic welcome that we have received here in Durban. It's wonderful to be here. So when preparing something to talk about, we discussed with Yinzi some, I was supposed to say something, right? About, there was something I should explain, right? Yeah, no Chinese language. Never mind. So we already forgot it. So I proposed some different things to talk about, and Yinzi chose this, which in fact is a presentation which I gave by invitation to the Nobel Committee and the Swedish Academy of Science before the summer. And so I thought, this group, of course, is full of eminent scientists, but not very experts in the field. So I thought this, you have to make it simple. And when you talk to them, And so therefore, I thought this is for a general audience could also be a suitable topic for today. So I will talk about the topic of fluctuation relations, on which I worked a bit. Angelo, who is in the audience, has also worked on the topic of fluctuation relations and related topics. And the plan of the talk is no, it doesn't work today. Okay, worked before. Okay, let's see, can we go forward? How do we go forward? Yeah, no, it doesn't work. Yeah, there's this one. Okay. Okay, we should try now. Okay. No. There you see. Okay. There's always something that can happen. Huh? Yeah. Now. Okay. I see all of you. Okay, should we try now? No. No. So I should do like this? Just a step manually ahead? No, it doesn't work. It doesn't work? Yeah. Okay. Maybe I can say something. So fluctuation relations, while you are fixing this, it has been a major topic in statistical physics over the last 20 years. So there was a reason I was supposed to talk, I was invited to talk about it. And I thought also at 10 o'clock in the morning, it's not the time for a completely, should I try again? Just a second. Yes, fine. Great, great. So we know what happened now. Okay, I see the beautiful audience. Yeah, wonderful room. But it's an advantage if I see my slides also. Just yeah. Where are they? I can see Tanya. Okay. Okay. Yeah, okay, this is, but can we move forward now? As checked for the keep launching. Maybe you're not screen saving now. Are you screen sharing? Will the people on Zoom see what I see? And what the audience sees? Yeah, share there. Okay. Okay, we will see. No, it still doesn't work. Can I? No, it does work. No, it does work. Are we interfering? It's just walking forward. It's not working backward. Backward is this one. Yeah. No. This is interference. I think it doesn't really. Yeah. Can you move back to the first one where we were? Now you're moving forward. Okay. So it's actually, the mistake was on my part, actually. The mistake was on my part later. I didn't realize that on this, you have two different buttons, one to push forward and one to push backward. So the outline of the talk, I will state the most famous fluctuation relation, by far the most well-known. And I will derive it using a little bit of mathematics, time reversal of the Kramers-Langevin equation, which for at least the physicist in the audience should be familiar. I will give a historical outline of most of the fluctuation relations. It's a wide field, and talk about the place of fluctuation relations in classical statistical physics. Then I realized when coming here and talking a bit to Thomas that quantum dynamics is a major field of interest here in Durban. So to make it a bit more personal, I will end by going a bit more technical on the quantum open quantum system side, and make an outline of a recent work that we did together with Giulio Chiribella and Karol Rzuczkowski, which I think though has relation to the topic of fluctuation relations. So fluctuation relations were achieved fame by far, this is easy to say, by two papers published by Chris Jarzynski now 25 years ago. And those papers contain the, let's see, now this pointer doesn't work like it did before, but you can see the equation says that you have the exponential of work, denoted W, in units of inverse temperature with kBt. So beta is the standard notation in statistical mechanics for 1 over kBt times T. Kb is Boltzmann's constant, T is the temperature. And the brackets means averaging. So you have a number of processes, and I will give some examples later, which kind of processes, for which you can measure the work, and I will give you a formula for the work. And then you do an empirical average, a sample average of the measured exponential of minus the work. And this turns out to be exponential of minus the free energy difference in the state, the initial state and the final state. And what you can see highlighted there is a blown up of a statement in the paper, which I will read to you. The free energy landscape between two equilibrium states is well related to the irreversible work, and that's the terminology used in this paper, required to drive the system from one state to another. So you have an exact relation, which is unusual and unexpected in far from equilibrium thermodynamics. And it's a relation between exponentials. And it's on one side, on the left-hand side, it's an average over non-equilibrium quantities. And on the other side, it's an exponential of difference between two exponential equilibrium quantities. So I will discuss this in, yes. The average is the, sorry, now I forgot this. The average is the sample average. You do the same process with the same initial conditions and you do it many times. That means that you pick the initial conditions of the process with respect to the initial distribution. In Jarzynski's equality, that would be the Gibbs-Boltzmann distribution, the equilibrium distribution. And then you run the non-equilibrium protocol with using the same deterministic change of the control parameter. And so you do it in the examples, which I will come to later. Maybe you do it 1,000 times, you get 1,000 values of the work, and then you take the sum of e to the minus these each of these values, and you divide by 1,000. And this is the average. Okay. Okay, so I'm talking about, I will discuss fluctuation relations in the context of time reversal. And to remind you, I have a reminder slide here of classical deterministic time reversal. I imagine that there is a control parameter here written lambda. It starts at the initial time, which is time 0 at some value lambda I, lambda initial, and it ends at the final time of the process, TF in this slide, at another value, or maybe the same value, but then let's say for this case, another value, lambda final. Then we know that in conservative systems, the Hamilton's equations of motion reads that the time derivative of position is the partial derivative with respect to momentum of the Hamiltonian function. And this is now a time-dependent Hamiltonian function because it depends on the time-dependent control parameter, lambda t. And the time derivative of momentum is minus the partial derivative with respect to position of the same Hamiltonian function. Now, so this is well known. This is undergraduate physics, and I think this should be also known to biologists and chemists and maybe even sociologists and economists in the audience, if there are any. Now, the tricky point, of course, the partial derivative of the Hamiltonian with respect to the position is what we otherwise interpret as the partial derivative minus the partial derivative of the potential with respect to position, so it's force. And the time derivative of position is momentum divided by mass. Okay, now the time reversal of classical mechanics with an external control parameter is that time goes to a new time t star, which is the final time minus time t. Q goes to Q star, which is the same as Q. P goes to P star, which is minus P. And if you do it that way, H goes to H star, which is the same, but with the changed time argument. Okay. And F star goes to F, also with the changed time argument. And this implies that the equation of motion of the time reverse dynamics has the same form, namely the time derivative of P star with respect to T star is F star, and the time derivative of Q star with respect to T star is P star over M. And we call this the time in reversal invariance of classical mechanics. Let us now imagine that we do not have a closed system, but an open system. So the most well-known, the most studied, the most basic example of an open system is when you add friction and noise to the Hamiltonian dynamics. And this is then known as the Kramers-Langevin equation. So it's the same equation. Now, it seems like the pointer doesn't work, but you can see. So you have Q star is P over M, and P star is not only F, there's also a friction force, gamma, P over M, and there's a random force with a random force psi dot, and then a prefactor which depends on temperature. And thank you. Okay, so I was just talking about these 2 points. Okay. Okay, so if I do the same time change on this stochastic differential equation as I did in the previous slide on classical dynamics, I would say T goes to T star equals minus T, Q goes to Q star equals Q, P goes to P star equals minus P, F goes to F star. But what does the equation go to? The equation goes to d dt star Q star is P star over M, d dt star P star is the force, and then there's a plus there. So there's plus gamma P star over M, and then there's a random force again. So the reverse dynamics, and there is an important paper published in 2008 by the late Krzysztof Gawęcki and his then PhD student Raphael Chetrit. They call this time reversal natural, but in many points of view, it's not very natural, because the time reverse dynamics doesn't have friction, it has anti-friction. And this does not arise from a macroscopic model of interaction with the bath. Yeah. So that is the first indication that there are some trickiness in doing time reversal of systems interacting with environment, which lead to friction and noise. You can do it differently. And in the same catalog of time reversals due to Gawęcki and Chetrit, you can also talk about canonical time reversal, and it's the same prescription, except that we now say that the friction force remains the same in the new coordinates. You could say that it means that gamma goes to minus gamma, but the main part is that this friction force minus gamma P over M goes to minus gamma P star over M. And if you do it this way, the time reversed equation is now a proper stochastic equation with a positive friction. So a process with another time reversal, a physical model has gone to a physical model, not to an aphysical model. Okay. Now, for this thing, there are some interesting consequences. And one of the interesting consequences, now the next slide will be the most mathematical of all my slides. So please bear with me. I'm going to talk about, to give you the context of the slide, I'm going to consider now the stochastic differential equation over a sequence of small time intervals. And I'm going to postulate what is the solution one time interval after another. Okay. And then, since this is a random equation, this is a stochastic force, the interesting question is the probability distribution that I go from one, or the probability that I go from one position at one time to another position at a time later. And position here means coordinate and momentum. Okay? Now, if I look at the whole path, I would have to add or actually multiply these probabilities from going from one time interval to another one. And here is the mathematics of this path integral, if you like, but in a completely well-defined subject. So the probability function that I have a history of Q and a history of P from the initial time to the final time, it says that at the next time interval, my coordinate is going to be my previous coordinate plus the small time interval times the velocity that I had. That's what the first time says. And the second one says that at the next time interval, my momentum is going to be my previous momentum plus a random term, and this gives a Gaussian distribution. So this all boils down to the formula here in this previous one. This is a way of expressing this particular term. Okay. And when you do this, we can compare this probability, the probability of this full path, with the probability of the same path, but in the canonically time reverse process. And that means I compare means I take the ratio of the two of them. And if I take the ratio of the two of them, I have the math in some backup slides, which will also be available in the PowerPoint. I find a very nice relation. So the probability of in the forward process, the original process of some history, compared to the probability in the canonically time reverse process of the history giving in the time reverse coordinates, is something which can be easily expressed in one way in terms of the changes in momentum and force and velocity. That it comes by canceling two different terms in a Gaussian, which can also be written in a more interesting way. Namely, we can identify this ratio, the ratio of the forward path probability to the backward path probability, to the exponential of the heat that is given up or taken up by the environment during this process, during the forward process. Okay, and the translation of this is quite simple. You can translate this. This is on the what we have here, and we can translate this by using the Kramers-Langevin equation, which is the forward dynamics. And you can identify this as being the force exerted by this. It's the reaction force exerted by the particle on the environment, and it contains the friction force and the random force. And here you have velocity. So force times velocity, here is force, that should be dt. This is work, and work done on an environment, that's heat. Okay, and this definition is due to a Japanese scientist, Ken Sekimoto, who is since long works in Paris. And it was first done 25 years ago, a little bit before the discovery of fluctuation relations, and it's also contained in his very well-known monograph published in 2010. So it means that for this model, and this is the template model for many further developments, entropy production, that means the change of entropy in the environment, can be defined in two different ways, which are equivalent in this model. And then for every other model where fluctuation relations have been discovered, it's in fact so that a similar equality is somewhere hidden. And one of the equalities is as a logarithm of a path probability in the forward process to the backward process. And in the other one, which is then a rather abstract quantity, but which you can use in different ways. But the other one is a rather concrete quantity. It's the work done by the particle and environment. So it's a negative of the work done by the environment on the particle, or on the degree of freedom described as if it was a particle. And this is what we call heat. So you can you can state very simple equalities in terms of these quantities, and then interpret them in terms of these quantities. And this is the gist of fluctuation relations. And here I have the two most famous ones. Both of them can, with this technology, derived in two lines. So let's start with Jarzynski's equality, which is the first one. Okay, let me try to do a particular average. And here I've cheated a little bit because otherwise they wouldn't fit on one line. So X stands for here Q and P. So let me integrate over initial position, final position, and Gibbs-Boltzmann weight for the final position, and the average over this entropy production in environment going from the initial position to the final position. Okay, and this of course can be interpreted now in two different ways. That's the gist of the point. Okay, so I can change this one. The average means the average over the forward probability. I can change this to average over the backward probability. And then it's an average over 1, where I go in the backward path from X final to X initial. And now X initial only appears at the final position here, which means I can integrate it out immediately. So it means that all I have is the sum, or if you like, the integral over the final position of this Gibbs-Boltzmann weight, which is the partition function at the final time, with the control parameters as they are in the final time. But then I can reinterpret the left-hand side to say, okay, this one here, I can take out the partition function at the initial time. I can write the Gibbs-Boltzmann distribution at the initial time. And then, of course, there will be a difference in energy between the initial time and final time, because I have to change this one to E minus beta E initial. So that comes here, and I have the same here. And then I use the thermodynamic identity that work is internal energy change. Work is related to internal energy change and entropy production. And then I have this equality here. Okay, so it follows directly. No, it is an equality. Did I say inequality? Yeah, but it is an equality. And it cannot be wrong because it's a derivation in 3 lines. Yeah, it's like a sufficiently short computer program cannot be wrong. Here's another one which is equally interesting, which shows you that this is mathematics. It doesn't really has to do with equilibrium or non-equilibrium. I can do another kind of process where I do not necessarily start in equilibrium, and I do not end up in equilibrium. Actually, I don't end up in equilibrium here either. But here I can say I don't assume that I start in equilibrium. Okay, so then I take whatever the final distribution is, and I do the same thing. Okay, and I can do the same thing, and I get a 1 here. Okay, and what does this 1? How can I interpret this 1? Well, I can say it is the average with respect to the initial conditions given then by the raw initial, whatever it is, and of the forward process of the difference of the logarithm of the probabilities in the final state and the initial state, and the same entropy production environment. So this, of course, gives you something. It's called the integrated fluctuation theorem due to Udo Seifert. And it says something of an exponential average of terms which are related to entropy. And it's easy to do by looking here that you can say from this one follows the second law. That means in expectation, the entropy of the system and the environment together increases. Okay, so both these derivations are quite short. Okay, so the observations: fluctuation relations in classical dynamics, sorry for the mistake here, emerge as some rules from time reversals, and this is so for classical fluctuation relations. And there's, of course, that's been a long debate, so that time reversals in open systems are not uniquely defined. And there are indeed different kinds of fluctuation relations, which you can relate to different kinds of time reversals. And the definite discussion of all these different options you will find in the paper the long paper by Chetrit and Gawensky. So you can say that for but the example here is, of course, mathematically, it's an example of a non-degenerate diffusion process. The different fluctuation relations are theorems for stochastic processes. So this part you could call not stochastic thermodynamics, but thermodynamic stochastics. These are thermodynamic properties of the theory of stochastic processes. Okay, so I will do some history. Who invented all this? Yeah. And so, of course, first we have to give the credit to Chris Jarzynski, who in 2 papers in 1997 derived his equation. First for a very simple case, namely a closed Hamiltonian system, and then for a more complicated case described by a master equation. At least in the West, these 2 papers launched fluctuation relations and to a great extent also stochastic thermodynamics as a major topic in statistical physics. But there are precursors. Well, maybe I should say there is an aside which was much discussed, which is important for the practical point, namely work in this sense has practical advantages compared to heat. Namely, that the work done in the equilibrium process, you can easily see, it must be the time interval of the derivative with respect to time of the potential. Okay, so if you have a control potential which has an explicit dependence on time, say a harmonic control potential with either change of the control point or of the spring constant, this is a rather easy thing to average empirically and to measure. And that's also been a rather important part in why Jarzynski equality is and remains the most well-known fluctuation relation. But there are precursors, and in fact, much earlier there were 2 in those days Soviet physicists Bochkov and Kuzolev, who published in 1997. They derived a result equivalent to Jarzynski equality, though only in the case of cyclic processes. So they did not, and I think it was just they were not interested in other things. Their derivation would equally well work for Jarzynski equality in the full sense. And I think, and also they related this to time reversals in open systems. This result is easy to say were not very well noticed in the time. They have written a nice review in 2013 where they discussed the different fluctuation relations and of course in relation to their own work. Actually, I looked for pictures of these 2 gentlemen, but they're not easy to find on the web. And at that time, they were both in Gorky State University in Nizhny Novgorod, it's in Russia. And later Bochkov moved to Donetsk University, which is in Ukraine. I believe, though, that they're both still alive. Then there is another relation, which is the relation due to Crookes, slightly later, working, at least discussing with Jarzynski. In my interpretation, at least, this is another kind of sum rule derived from forward and backward processes, and it's easily stated in the following way that the probability of observing minus the work in the time reverse process divided by observing the work in the forward process is an exponential which depends on the work that you're looking at, the free energy difference, and in units of kBt. Okay, so this is, as we will see later in an example, quite convenient when looking for, when using this for experimental data. It avoids some of the problems of sampling that you have in Jarzynski equality, and therefore this equation is the form which has been most widely used. Okay, then for stochastics, since my example, where these are all easy things, is for stochastics. Credit should be given to Jorge Kurchan for the discovery of fluctuation relations in stochastic processes. There is a little later paper, which is more readable, still not quite easy. And then there is the long paper of the late Krzysztof Gawęcki and Raphael Chetrit. But I think this is the definite treatment of fluctuation relations for stochastic processes. I believe still is. Okay, so Thomas, you have to tell me how I'm doing on time. Nobody's telling me to hurry up, so I'll continue a little bit on the place of fluctuation relations in statistical physics. Yeah. So stochastic thermodynamics is and has been an extension of thermodynamics to the mesoscopic domain. It concerns systems where fluctuations are important. So it's not systems that are thermodynamic, that are large in themselves. And this means that heat, work, efficiency, entropy production, and similar quantities all fluctuate. However, in almost all settings that one has been of interest, the system, it's a system that's not large. The environment with which the system interacts is a thermodynamic bath, and heat bath is in a thermodynamic system. Here are some examples of such systems. Here's the famous ratchet and pole of Feynman from his lectures, which was analyzed later by Juan Parondo and Pepe Español in a very, very nice paper, where especially the concept of efficiency of this motor was discussed in a very nice way. Turns out, in some sense, one can say that Feynman cheated in his lectures. The story is more interesting, and I recommend for those of you who want to get into the field to read this very nice paper of Parondo and Español. I will talk a little bit more about this example in the next slide, and this is an example from my colleague in Finland about an experimental device to consider similar things in the quantum level. It's from the lab of Jukka-Pekkola in Helsinki. And molecular unzipping, it has been one of the major examples. So here is an image of a DNA. Here's an image of an RNA. Here's an image of a protein. And here's some different, say, high-profile publications of these cases. So the idea is to attach the ends of the single molecules by biochemical means to a bead, and this bead can be moved by laser tweezers techniques, and so the equilibrium point of the two ends of the molecules can be shifted. And this you can do slowly, of course, but you can also do it relatively quickly. And that means that you change the equilibrium point, you change the potential at the time scale, which is on the order of, or maybe faster than, the natural relaxation time of the molecule. So you really do have a non-equilibrium process where you pull the molecule apart. But since you know the equilibrium points at each time where you pull the molecule apart, but you can also observe where are also these beads, so you actually know where they are. You can derive from the experimental data, that means the time course of the actual position of the bead which you use to pull apart the molecule, and the control parameter, which is where you would have liked that bead to be, and where it would be if you would wait for a long time at that control parameter. You can get the non-equilibrium work in these circumstances. You could do it once, then you can put it back. Then you could do it once, and the best experimental teams are more or less able to do this 1,000 times before the molecule breaks. So you get the statistic from 1,000 times. If you do something equivalent in the solid state domain, which was I pointed to in the previous slides, you can do 1,000,000 or 1,000,000,000 times, and you can get fantastic statistics. But then that is has not had the same impact on the field as these experiments. So you can do this, and you can verify. For instance, here's a verification experimental by this is Félix Ritort, who has been one of the pioneers of these single molecule techniques, and it's an experimental verification of Crookes relation, because you would have the logarithm of the ratio of the forward and the backward probability with different work should be the work minus the free energy difference divided by KBT. So you take the logarithm on the left-hand side, you have a linear function on the right-hand side, and so you get a linear slope. And indeed, here's the logarithm of the ratio, and here you have a linear function. And you can see that this is a quite good linear fit. Okay. So this is maybe I should say something. Before going here to quantum, let's say practically, when has this been useful? Okay, for which molecules or for which properties of molecules can you get results in this way that you cannot easily get other way? It turns out that this is mainly for the free energy, the change of the free energy change. So if you make a change to the molecule and you compare two different molecules, which have slightly different molecular composition, you made a change in one point, then you can make this delta delta F, you can estimate in this way more precisely than any other way. And there's a related techniques to look also at knots and the properties of knots as traps to the folding of molecules, which I believe are also at this time leading. Okay. I don't think so. Well, I don't know. There's no R value in here. Actually, you know, I got this slide from Felix Retort, and surely he published the data with an R value, but here there's no R value. You can guess yourself, you know. I mean, we are practitioners of the art of estimating slopes, aren't we? Yes. Yes. So what would you say? Is 0.0? It's 0.04 here significant or not? Probably not, right? But actually more or less in the limit, no? Okay. There's actually a lot of technical details going into this, which you can read in the papers. There is the issue of there's not only the molecule that you pull apart, there's also the connection between the molecule and the handles, and the handles can sometimes also have a free energy. So all these things can play a part. Yeah. Okay. So with this, I go to the last part, if it's quantum fluctuation relations and time reversals for general open quantum systems. So now I change gears a little bit. I think I presented to you the case that fluctuation relations is an important part of modern statistical physics, both theoretically and with practical applications. And I'll tell you now a little bit more about my own work, or a bit more on the theoretical side. I heard this was perhaps of interest. Yeah, also gives a more up-to-date touch of the whole thing. Okay. I have 10 minutes. I think I can do this in 10 minutes because, yeah, okay, either you understand all of it and then that's the case for you, or you don't understand so much, but then you can relax and look at the slides. So, okay, Angelo, for you. This is a rehearsal of quantum evolution, a crash course for the non-quantum people. That's somebody like you, right? So then we know that the qubit is a two-state system. Okay, you remember? Yeah. And then a physical state is a complex ray, unit ray in, yeah, okay. You're familiar, right? A pure state of n qubits, a complex ray in Hilbert space of dimension 2n. It has then 2 to the 2n minus 2 parameters, okay? Okay, yeah. And a mixed state of n qubits is a density matrix. This is a completely positive operator of trace 1, Hermitian completely. It has 2 to the 2n minus 1 real parameters. This is another way of saying d squared minus 1. Okay? And if you have a unitary evolution of n qubits, symbolized by matrix U, it of course has the same number of parameters as the Hermitian. So that's also 2 to the 2n minus 1. Okay? Now, if I have a general evolution on n qubits, that's given by, in this case, 2 to the 4n minus 2 to the 2n. So that is d4 minus d2. Okay, so usually if you're not a quantum person, which was my case, you sort of know anyway everything up to here, but then you say, oh, this I don't know. Okay, so there is some point where the quantumness starts to come in. Okay, so the general evolution on n qubits, which is then a completely positive trace preserving map, usually denoted by big phi, has many, many more possibilities than unitary evolution. There's much more, and this would be including, say, in the classical limit, friction, noise of many different types of friction, and probably many kinds of of changes which cannot really be described as friction at all. So fluctuation relations in quantum systems hold in isolated quantum systems, and you can prove this in 2 lines without using time reversals. This is in closed systems, okay? So I start with an equilibrium state. This is the diagonal state in the basis of the Hamiltonian, and here's the Gibbs, here's the Boltzmann weight, okay? And I go to the end, and I go to a final state, which is a final density matrix, which is a unitary quantum map acting on the initial state in the diagonal state. So this is, I mean, I pick one of those, one of the initial states, and this is the final state. And when I measure it, I get the final state. So on an isolated quantum system, the work should be the difference in the energy. This is called also the two measurement protocol, the difference in energy in the final position minus the initial position. And there is a unitary time development implies that the map of the unit operator is the unit operator. In other words, the unitary maps are unital, okay? So here you can do one, you can say this average, okay? I write this average in the quantum way, sum of the initial state, initial energy, here's this one. And I have the sum of the final state and the matrix element of the time evolved initial state, and then there's this matrix element on both sides. And here I have the work, okay? So, but when I do this, I have that this operator, I take the sum over, I take this EI here and I cancel this one, okay? This means that EF still remains, but there's no dependence left on the initial state except inside. But then I sum over all these states, and the sum of the all states inside is the unit matrix, the unit operator. And so then the map of the unit operator here is unity. And so then I have the matrix element of unity. Okay, and then that's F, that's just one. And then so all that remains is the sum of the final states of e to the beta e final, and that's the definition of the partition function in the final state. So this average is the ratio of the partition function in the final state to the initial state, which is the e to the minus beta, the change in free energy. And this is another. In fact, this is Jarzynski's original derivation in the classical domain, just stated in the quantum domain. It's the same. Okay, and that is contained actually in a more convoluted way, but it's contained in this paper. And so you can imagine then that open quantum time reversal should be discussed on the level of maps, super maps of CPT maps or on quantum channels. So let's assume that there is a time reversal that maps a forward quantum time dynamics to a backward time dynamics, okay? So let's call this operator, this supermap R, or super operator R. It should be an involution. That means it should map every quantum channel into another quantum channel. And if I do it twice, I should come back to the original one. That's a requirement. And for unitary time development, it should agree with standard quantum mechanical time inversion defined on closed systems. Okay, so if I do this, I can play exactly the same game as I did with the classical case if I define an entropy production functional from the initial state to the final state as the logarithm of these two sandwich, the ratio of these two matrix elements. And then this is in fact in the quantum domain, it's the same derivation of Jarzynski as I had before in the quantum domain, in the classical domain. Okay, it works exactly the same. But is this log ratio of matrix elements and entropy production? And if it is, in which sense? So of course there are specific examples of fluctuation relations in open quantum systems which are known more than a decade. But the general theory of quantum fluctuation relations has not been found. And there is actually no reasonable way in general to attribute this to an entropy production in some environment, even though there are reviews by eminent scientists who claim that there is such a theory. And for instance, this one, which is now a bit old, of course, but yeah. Sorry? No. Okay, so why is this? Yeah. And why is this? So here's at least an attempt, a recent attempt to understand why this should be. In quantum, we can put the additional requirement that the time reversal operation of the open quantum systems dynamics has to be a linear supermap. And for those of you doing quantum foundations, which I realize is, for instance, you know very well that there is a large literature represented, for instance, by the group of Bruckner in Vienna, investigating supermaps. And if I go to the more properties of supermaps, the more brave Italian school, there is an infinite chain of supermaps and supermaps and supermaps and so on. Maybe that is why Kiribella had to go to Hong Kong to get the job. Yeah. No, this is a joke. It's a bad joke. Sorry. I hope this goes live. I apologize to everybody watching this both live and in real life. Okay, so if we take this, we can say it's a mathematical problem. We have a very large space, and can we have a involution that acts linearly and which when it's acting on unitary time evolution corresponds to standard quantum mechanical time reversal? This is a well-posed mathematical problem, and we can refer to the experts in quantum foundation saying that it's a necessity that that it has to be, the supermap has to be linear, that otherwise there are problems. We can accept their point of view in this way. Is it possible? It's a mathematical problem. And there are two theorems now. I guess I'm in the last 2 minutes. So let's say there's a main theorem which we managed to prove in this paper on the level of quantum operations. So this is not trace preserving. These are trace non-increasing maps. So it's a slightly bigger space of evolutions, which is easier to work with. And this main theorem has as a consequence that there is no such time reversal. Okay. And I hope this maybe can be a starting point of discussions of interest with the quantum information and quantum foundations group here in Durban. So I come to the summary and outlook. Fluctuation relations are identities in classical open systems that hold arbitrarily far from equilibrium. I did not cover this aspect, but very famous near equilibrium identities like fluctuation response and Onsager relations can, if you frame it in a favorable way, be seen as consequences of fluctuation relations. Of course, it's a system which can be arbitrarily far from equilibrium. The environment remains close to equilibrium. And fluctuation relations, especially Crookes theorem, is a data analysis tool. And the most important application so far has been determining folding free energies, or in fact, delta of folding free energies of biopolymers from single molecule pulling experiments. So that's getting an equilibrium number from non-equilibrium measurements. In classical open systems, the fluctuation relations follow from time reversal. In quantum open systems, there is no general theory for fluctuation relations. And maybe that's the end of this talk. Maybe that's so, because there is no general quantum time reversal acting as a linear involution. Okay, there is a caveat that the theorem, we have not been able to show it for quantum channels so far, only for quantum operations. But presumably it will hold also for channels, which is a more complicated space. And with this, I thank you. And I thank the people I worked with on aspects of fluctuation relations over the year, and more recently, Julio Kiribella, Karol Rzeczkowski, and also Jakub Zakrzewski on the quantum side. And of course, we have to thank the Nobel Symposia for bringing all of us to South Africa, and also for being the reason we are here today. Thank you.
So is there time for questions?
Yeah, I think there's a button to push. Yeah.
Probably a little bit stupid question. Did people try to use replicas in this kind of?
You mean in the spring glasses sense?
Yes.
Not as far as I know. Maybe Angelo is different. I don't think it's been used
for the average, right?
No, I don't think so. No. There is an integration over the realization of the stochastic process, which is a source of disorder, but not in the same way. It's not quenched disorder.
But quenched.
Yeah. Mm-hmm. Yeah.
So I see a lot of this discussion is to do with a thermodynamic process in the thermal equilibrium or quasi-equilibrium system. I wonder, did someone looking at this relation in the gravitational system as the
gravitational system,
Yeah.
like black holes or something.
Yeah.
There are some Japanese group. There were some papers I read a few years ago that tried to use this in the context of Hawking entropy. It can probably be, if you Google Jarzynski equality black holes or something like that, there comes up. There was some 3-4 papers. I don't think they really achieved anything for black holes, but of course they managed to translate one concept to another one. There is the issue, of course, what is the environment for the black hole? What is the heat path? Yeah, if the heat path is the vacuum, that is a very complicated influence on the dynamics, which is not Markovian, for instance. So I mean, there are technical issues. Yeah.
There's a question online from Muzi. So he says, so looking at the concept of time reversal, especially when I see it in relation to molecular unzipping, does this mean we are on our way to finding even more accurate ways to trace the evolution of species using DNA?
It's a difficult question. There has been an effort in the literature to do this. The person mainly one usually refers to is Jeremy England, who was a student of Jarzynski. I would say these are attempts to relate this, but I wouldn't say that they actually solve anything. But they certainly achieved quite some there was quite some attention given to them. Maybe something like a bit more than 5 years ago. Yeah. Doesn't mean that somebody else maybe can get results which, for instance, I would consider more practically useful. But yeah, certainly was a great hope for a while. Yes.
Thanks.
Still have 5 minutes for questions, so you are encouraged to think. Question. In the meantime, I'm going to ask a question myself.
Yes.
So, if I understood this correctly, then you are basically saying that if you look at operations in quantum mechanics, which means that you are you could think of measurements, for example, and you could think of interaction with the environment, that you then cannot find a map that describes the time reversal with the mathematical properties that you think it would need. And why? I mean, I wouldn't be so surprised, because I think that if you have such a measurement or interaction with the environment, you are losing information, and therefore you cannot get back. Or is this a too naive way of thinking about this?
Naive is not. I don't think that's the issue, but I think that the problem is the statement of the statement of the problem was a little bit different than you say. So I can say, let's suppose I have a time reversal that let's suppose I have a map that depolarizes completely. Okay, so that of course the map loses all the information that I have in the initial state. Okay, then the question is, what is a time reversal of this one? Okay, of course it cannot be to take the information which is now destroyed, which is now disappeared, and go backward and find it again. This is not a time reversal of the completely depolarizing channel. But you can say another depolarizing channel is also a completely valid image of the operation of time reversal, and that maps quite well with the stochastic process example in the beginning. I start with the stochastic process with friction and noise, and I do a time reversal classically in that case, and I end up with another stochastic process with friction and noise. Okay, so I could say, okay, I have lost all the information of all particular states, but the channel, the depolarizing channel, can have a time reversal, which is, for instance, another depolarizing channel. Yeah. So the statement is that there is no, but then what properties do I have to have of this map of channels to channels for this to be a valid time reversal of open quantum systems? So the first one is it has to be an involution, which means it should be defined for every channel. And if I do it twice, I should get back the initial one. And in the trivial example, which I just gave you, that works because I start with the depolarizing channel. I map it to the depolarizing channel. I do it again. I am at the depolarizing channel again. Okay, so that is fine. Then it should be, if I now specify this map on which should be defined on all channels to unitary channels to closed quantum systems, it should work in the same way as time reversal that you read on in more or less elementary quantum mechanics. That means I change the role of U and U dagger. Instead of having rho going to U, rho U dagger, I should have rho going to U dagger, rho U. Okay. Now you can imagine that this is possible to take together the depolarizing channel. In fact, it is possible to take this map of depolarizing channels to depolarizing channels, because that is a unital map. And there's a special statement saying that the space of unital maps, there is such a map. Okay. A linear transformation that takes every channel to every other channel. If I specify to unital channels, it works. But if I go beyond unital channels, actually, we are not quite sure, because we haven't proven that there is no such map on channels and channels, from channels to channels, but there is no such map from quantum operation to quantum operations. And that is the statement, which acts linearly, of course. Yeah. Mm-hmm. Question? Yes.
Oh, so can you maybe go back to slide 6?
I don't see the slides myself anymore.
So that's factor of gamma in the last two terms.
Maybe I should try to go. Somebody should. I don't see the slides myself. I don't think actually I am in charge of the slides. Huh? So okay, you can ask the question and I remember the slides, but maybe the audience don't remember the answer. But okay, what is the question?
So on slide 6, you had a energy loss term.
Yes.
There's two terms.
Yes.
So why is gamma a part of both of those terms?
That's called the Einstein relation. They have to be. And that is a part of the relationship between friction forces and random forces that you have with interacting with a heat bath.
Okay.
It's also called the detail balance condition. Yeah. That's.
Okay, if there are no more questions, then I would like you to thank the speaker again, Erik Aurell, for the wonderful talk. And it's my pleasure and honor to give you this present in the name of the School of Chemistry and Physics. And thank you again for coming and for sharing your expertise with us, and also for connecting us to the outside world. Thank you very much.
Thank you, Thomas. It's been a pleasure. It is a pleasure. It's still a pleasure. Thank you.
Okay, so the next speaker. Great. Yes, please.
The space. So if it's operations should be okay. Okay.
Just information. Okay.
Yes. Yeah. So now
That's India.
Yeah,
Does it look good? See if we can change the slide. Yeah, cool. Okay. Perfect. Thank you. Thank you.
Okay, so it's my special pleasure to introduce. I'm sorry. It's my special pleasure to now introduce to you Professor Luca Gammaitoni. He's from the University of Perugia, and his special subject or specialty is noise. And when I asked Professor Gammaitoni whether he is an experimentalist, he said to me, look, it's Feynman said, there are theoretical physicists and then there are physicists, and he is a physicist. So it's a special pleasure. I just want to say that I admired what Luca told me. One of the projects, I think it's even a startup company that you are building, is working with sensors that get their energy from the environment. So, for example, he has a sensor that investigates or measures the vibrations of a bridge in order to see whether the bridge is about to collapse. And the energy it needs to send the data to somewhere is actually coming from the vibrations themselves. So you can have intelligent solutions that really kind of are self-sustaining and don't need energy from outside. And since I'm a big fan of Kuckuck clocks, of mechanical systems, where usually you only have to put in a little bit of work yourself, and you don't need batteries, this is something along my line. So thank you very much. And please put your hands together for Professor Aurell. But before we go to your talk, may I ask Professor Ma to introduce your bio?
Hello again. So yeah, let me introduce Professor Luca Gammaitoni, a director of the noise in the physical system laboratory at the Department of University of Perugia. Right? So by the way, I'm disturbed by noise. So you're going to provide a solution for me. Okay, so Professor Luca Gammaitoni is a professor of experimental physics at the University of Perugia in Italy and the director of noise in the physical system laboratory. He graduated at the University of Perugia and obtained the PhD in physics from the University of Pisa in 1990. Under the Lin Tower, by the way, Pisa is the good place. Since then, he has developed a wide international experience with collaboration both in Europe, Japan, and USA. And in 2016, he has been awarded the Spectral Breakthrough Prize in Fundamental Physics for the observation of the gravitational wave, opening new horizons in astronomy and physics within the LIGO-Virgo consortium. He authored over 350 papers on top-level scientific journals and field books. He is also the author of 10 patents for industrial application. So let's welcome Professor Luca Gammaitoni.
Thank you so much. After this introduction, whatever I can say will be not enough. Okay. Okay, I'm so glad to be here, and just relax. My talk there will be much less mathematics. Hopefully, it will be as interesting as my colleagues' talk, but on a completely different topic. Well, first of all, I want to tell you something about the place where I come from. That's Italy, and Perugia is a town right in the middle of Italy. It's geometrically between Florence and Rome. It's the capital of Umbria, which is the small region designed there. And it has a border with Tuscany, which is usually very famous. And Perugia is the site of a very old university. It was founded in 1308, so it's more than 700 years old. And this is my group, the Noise and Physical Systems Laboratory. It's about 10 people. And if you want, you can find further information on what we do on our website, which is www.nipslab.org. What we do in this lab, well, we do a number of things, actually many different things, all more or less associated with the idea of fluctuations and noise. This is a list of European funded projects that we coordinated or participated in the last, say, 10 to 15 years. And basically, we are interested in energy transformation at very small scale, where small scale means that the power is significantly below 10 milliwatt and volume is significantly below 1 cubic centimeter. But now let's come to the topic of the talk today. So the title is why it is difficult to find something if you do not know what you're looking for. This seems to be a joke, but actually it's quite a common situation. Sometimes you have to find something, but you don't know exactly what to find. This is a condition that nowadays is becoming more and more popular with this big data approach, when we have so many data available and we do not know what to do with this data. This is one of the topic, as been mentioned, I am also the founder of a number of startups. One of the startups, which is called Wise Power, work on the topic that Thomas mentioned before. And now we have accumulating a number of data, a lot of data from vibration, for example, building vibration. So people start saying, okay, what can we do with this data? What can we look into those data? Okay, so plenty of data everywhere. The idea is that they must be worth or something. There is people who is also talking about the data are the new oil. Okay, so it's something which brings you wealth, value, if you know how to exploit this data. So this is the big data scenario. And you have seen that in many of our universities, we have already started these courses in big data analysis. And sometimes they are, of course, merged with artificial intelligence course or with, say, machine learning techniques. Now, I am old enough to say, I can say that we are actually assisting at a change of paradigm. Sometimes this activity on data is coming to influence our understanding of the natural things. So physicists are the people, among all the others, that are more curious about natural things. And we want to understand the fundamental laws of nature. This is what they told me when I started to study physics. So let me give you what is the traditional or the Galileo paradigm on this. Well, let's look at this picture. Okay, this is something that you can observe when you go out and you see this beautiful person on a swing, and she's swinging. Now that more or less what probably Galileo saw when he was thinking of the pendulum. There is a long road from this picture to the pendulum. What is this long road? Well, first of all, you have to decide what is the phenomenon that you want to describe. What are you looking at? Maybe you are simply interested in monitoring the temperature of this woman, or you are interested in seeing how the hair moves, or how the the color of her skin change with time. So you have to decide what is the relevant quantity that you want to pick up. I'll show you an example afterwards in which this process is detailed. But what I mean is that there is a long road to go from a phenomenon to a physical model. That's a physical model used by Galileo. I mean, the extreme complexity of the woman on the swing has become a single ball, actually a material point, that moves on a circular trajectory. And you are interested in monitoring the angle of this ball, the angle that the vertical does when it moves around the vertical, possibly for small oscillation. So, I mean, can you understand how difficult or how complicated is the compression of the huge complexity of the phenomenon towards the model? So this is what physicists do. This is what we have been doing for many, many years. We have been observing natural phenomena and trying to guess models which were able to capture few aspects that we believe are relevant for the description of the phenomena. On doing this, of course, you lose a lot of information, of course. We do not know what color are the eyes of the girl or what is her temperature, but those are immaterial for us. We are fixed on measuring the angle. Okay, so this is the Galileo approach. Now, what is the big data approach? Now, there is a different paradigm, or somebody claimed that this is a shift of the paradigm. Now, the approach is data mining. What is data mining? Well, clearly, it's a mining activity. When you do a mining, you go inside a mine, underground, and you look for something. Maybe you know what you're looking for. Maybe you're looking for diamonds. I know that this is popular in this place. Or maybe you're looking for copper or iron or something different. But you simply go inside something and try to see what you can find. And maybe you find things that you don't know what they are, and you bring them out. So that's the paradigm now that is proposed to us. Am I joking? No, actually, there is people who takes this very seriously. This is a paper from Wired. And it says, the end of the theory. The data deluge makes the scientific method obsolete. So there is a clear attempt to change the paradigm on how we do model, how we make model for explaining the natural things. Okay, so this is one thing. There is another thing I want to tell you. Before, Janze has mentioned that I've been working on gravitational wave detection for a long time, and that's true. We got this beautiful prize. My colleagues and friends like Barry Barish got the Nobel Prize for this. So I've been working something like 25 years on building gravitational wave detectors. We, of course, were very much into the noise aspect of the gravitational wave detectors. These are very sensitive instruments, and the noise is very important, of course. So this is a picture taken in Perugia. Soon after, 15 September 2014, it was the first observation of gravitational wave. Soon after, there was the Nobel Prize that was awarded to 3 persons. Among them, there was Barry Barish, which was the head of the experimental collaboration, LIGO Virgo, which was a very large collaboration with about 1,000 people involved. So after the Nobel Prize, I invited Barish to come to Perugia and to give a public lecture. At that time, I was the president of the foundation of the Municipal Science Museum in Perugia. So we organized this kind of outreach event, as you do very well also here. Barish came to my place. We organized this public lecture, was extremely popular. A lot of people, we were in a very big room, but we had to let people out because it was extremely popular. After the lecture, we went to dinner. And when we were at dinner, we were chatting. Of course, I knew Berish from a long time because I was part of the collaboration. I said, now, what are you going to do now? So Berish was telling me, look, now we think that we are going to try something different in order to find information inside the gravitational waves. Just let me show you. These are the signal of a gravitational wave. This is what we measure with the instruments. This is a typical phenomenon of a coalescence of, for example, two black holes. So the two black holes come close, and then they start rotating around each other until eventually they collapse. So there is a sort of explosion, they merge actually. And there is a new black hole. During this phenomena, this merging, a huge amount of energy is released in the form of gravitational waves. And these waves travel for million of kilometers, and many also million of years. So after some billions of years, you can actually observe the gravitational wave when they come close to you. So how is a gravitational wave detected? We have an idea from the theoretical study of general relativity how the signal should be. Okay, so now you have the measurements from the interferometers for this, from this gravitational wave detectors, and the measurement is a mess of noise, of course. It's a time series usually of the distance between two mirrors, and you're looking if inside this time series there is some oscillation like those that you see there. This is a very hard search. It takes time, it takes effort, it takes a lot of work to optimize your detector, but eventually we succeeded. So those are the wave forms that we were looking at for detecting gravitational wave, because we expected that the merging of two black holes could be a strong signal. Now, many of these signals have been observed since then, many, in the last, say, 8 years, many signals. There is a catalog that's published. You can go and check how many. And now Barry Barish was telling me, look, what we want to do now, we want to go back to the data that we have already analyzed to see if there is something else. Because we have been taking data for 8 years. So we have plenty of data. And we want to see if there is something else inside. What else? He said, we do not know. We yet do not know. But now we're going to use artificial intelligence. We're going to use machine learning technology to see if inside those data, there is something that we do not know. A new form, a new waveform that we do not expect, a new kind of physics. Maybe there are other phenomena different from black hole merging or star explosion, maybe phenomena that we do not even know. They generate a gravitational wave, and we want to discover this new phenomena. So that was the dinner. And I was kind of perplexed. So I thought about this for a couple of weeks, and then I wrote back to Barish saying, look, I think that what you want to do is not possible. You're not going to get any new information out of your activity. And there is a very good reason. And let me explain you this reason. So we started a conversation. I'm not sure that I convinced him, but certainly he was listening to me. Now I want to go to tell you why this is not a good approach. And there is no hope to find something unless you know what you are looking for. Okay, so this is a very bearish statement. And so the idea of looking for something which we do not know if there is and exactly how it is not new, actually. This idea was already around a number of years ago during the beginning of so-called chaos theory or chaos studies, and especially around the 70s and the 80s of the last century, and the work of Dutchman Floris Takens and David Ruel was focused on this. At that time, it's the question was, is there any attractor, strange attractor inside the data that I'm measuring? The data that I'm measuring are just random noise, or they come from a dynamical system that is moving in a very complicated way because it's chaotic, but it's not random. There is a dynamical system behind. So that was the idea that we're looking for. And so there are a number of good reasons that they developed. And if you want to look at this good reason, there is a nice paper by Professor Angelo Vulpiani here and Heike Osni. It's called Forecasting in Light of Big Data and has been recently published. I want to give you, these are mathematical reasons, very, very strong and interesting mathematical reasons. I want to give you a flavor of this reason by mentioning a work from the literature. I don't know if you are familiar with the work of the great Argentinian writer, Jorge Luis Borges. Borges, it's a writer. Now it's dead, but it's our contemporary. And he wrote many interesting novels. One of these novels is particularly interesting, and it's called The Library of Babel. Have you ever heard of it? Nobody? Good. Okay. I recommend everybody, you can go, you can stop this lecture, go out and go reading this book. This is the most important thing you have to do. Way more important than listening to my lecture, okay? This is a novel. It's a very short novel. You can read it in 1 hour easily, but it's very beautiful. And the reading of this novel will change your life. I can assure you. Your life before and after the reading will be different. There are not many texts like this, huh? Okay? Maybe there are some texts from the traditional religions, of course, but not many texts in your experience will be like this. Before and after, you will be two different persons. So the novel is about a library. A library is a place where there are books, of course. So the library that Borges dreamed about is a huge library. And this library, of course, contains books. But if you open one of these books, you do not find easily a readable text. You find simply a set of letters, actually all the 24 letters of the alphabet, plus some punctuation, but they are all mixed together. They are randomly disposed along the book. So the novel is very poetic. So I strongly recommend you to read it. You can read it in English. If you know Spanish, read it in Spanish because it's beautiful. So the idea is that the books in the library, they contain all the possible combination of letters. How many are these? They are a huge number. So if you take the 24 letters of the alphabet and you mix them together and you measure, count all the combination possible, this is a huge number. So, and then you collect all this combination into books. Every book is different from the other. There is no repetition, I can guarantee you. And you have a huge number of books, but still a finite number. Say like billions of books, okay? But still a finite number. So in principle, a library like this can be built. In principle, this can be done, especially with our information and communication technology instrument nowadays. So the Library of Babel was a dream at Borges' time. I think the paper, the novel was written in the 40s of last century, almost 100 years ago. Nowadays, in principle, we can make it, okay? So the Library of Babel really looks like the big data paradise. Think for a moment. There must be a book somewhere that tells the story of your life. The story of your life since the day you were born, what you did, which school you went, and eventually how you will die. There must be a book like this, right? In principle, yes, of course, because it is writable. This is a story that you can write. So if I take all the combination possible, there will be a book that tells this story. But not only one. There will be hundreds of thousands books in which there is only a small variation. For example, a word, which is different from the others, but the story is the same. And then there will be, at the same time, a huge amount of books that tells a different story. Which one is the real story? Which one is true? That's crazy. I mean, if you think about it, this is like a vertigo. You can get crazy thinking about this. So I strongly recommend you read this book and think about this, because this is going to change your life, your perspective. Now, the Library of Babel contains all the possible information. So the problem now is just extracting this information and finding the information that is relevant to you. There is a book that tells what is going to happen next week, how the stock market will perform next week. Certainly there is, because there are books on stock markets, of course. There are records on all stock markets events. So there's certainly a book in which the stock market of next week will be described. The point is to find it. Now, let me give you an example that tells you why you will never be able to find the book that tells the story of your life. Let's look at this sentence. Okay, this sentence is in English. While the music goes, Alice and Bob exchange secure messages through their entangled spins. This is a sentence contained in one book. Okay, I open a book, and in the middle of a mess of letters, I found this sentence. Whoa, that's beautiful. Now, question is, what is the meaning? What is the meaning? Well, it depends. It depends. The two words entangled spins may indicate two very different things depending on whether you interpret them using a 19th century English dictionary or a 20th century one. In the first case, the phrase would indicate the confidences that two lovers exchange, perhaps whispering mouth to ear, during a waltz tour. That makes sense, right? That's what's happening. These two lovers dance. Maybe they are illicit lovers. Maybe they need to whisper something to each other while they are dancing, because maybe that's the only chance that they have to come together, close together. This is a possibility, right? But there is another possibility. If you use another dictionary, more recent one. In the second case, what sounds like, while the music goes, Alice and Bob exchange safe messages through quantum cryptography. That's exactly what is reasonable, could go, right? Same sentence, two meanings. Which one is the true meaning? That's impossible to say. Because it is true that you have all the combination of letters, and these are an infinite number. So you have a finite number of books. But the meanings that you can associate to each string of character, the number of meanings is not finite. It's infinite. There are infinite meanings for each string of character. That's the terrible news. You will never be able to find the book of your life or the book of the stock market tomorrow, because for each string, there will be infinite number of meanings. The meanings are many more than the string of character, an infinite number more. Okay, let's move on. So this is again Borges. It's a sentence from Borges, very, very poetic. But eventually, you should realize that the number of meanings that can be attributed to the text of those books is infinite. And therefore, this infinite amount of meanings cannot be contained inside the books. The guy who discovered these things is this guy. It's Jules Antoine Richard. And this is called the Richard paradox. So the fact that to a finite string of character, you can assign an infinite number of meanings. And if you want, this is one of the original works that eventually helped Gödel to formulate the indecisibility paradox. Okay, so in our case, having a certain set of data available is equivalent to having the potential answer to an infinite number of physical problems. That's the problem that LIGO and Virgo will have. They have the data, but they do not have the answer, the questions. So the data are the answer to a possibly infinite number of questions. For every possible answer, there is an infinite number of perfectly compatible questions. What is the question that you are interested in? It's impossible to know the answer if the question is unknown to you. That's the sad truth. So there is no algorithm, no machine learning, no artificial intelligence, no computing power that holds, however large it may be, it will not be able to find the answer to unknown questions. That's why it's impossible to find something if you don't know what you're looking for. If you want to read more or listen again to this story, you will find this is on the web available. There is also a link, but if you go on medium.com and you put Gammaitoni in, you will find it. Now, let's try to move on. I don't know if you're familiar with the book, The Hitchhiker's Guide to the Galaxy by Adams. That's a beautiful book. It's very funny. Not as important as Borges' novel, but if after reading Borges' novel, you're still alive and you have time, you can go and read this book. So at the end, you remember, the people who have read the book, there is this... Right. But Douglas Adams, it's a great in his own field, but certainly not as great as Borges, but you are right. Okay, so this at the end, I mean, the story is they built a huge computer. In this book, in this novel, they built a huge computer that has to find the final answer to the question of the universe and everything else. And the computer computed for many, many years. And at the end, the answer is 42. So, okay, the answer is 42, but what is the question? Nobody knows. Question is lost, and so it's completely useless. Okay, what has this to do with the work of physicists? Well, of course, it will be a little frustration for Barry Barish and my colleagues, but I think that there is something to teach us also about our work. So how do we build models of the universe? How do we build models of physical systems? Just let me give you an example of what I mean. Let's suppose that we are interested in building a dynamical model, meaning something that has to do with the motion. So let's suppose that you have a bunch of stones or pebbles like this one. This is our system. And then we have a phenomenon. For example, we want to launch the stones possibly in the water or something like that. So we have a system and a phenomenon. And how do we describe this phenomenon? As I said before, just like Galileo did, we need to decide what's worth, what is interesting for us. So we need to decide to start asking the questions. This is the niche, the start of our process. What are the questions that we want to ask? Meaning, what are the relevant features that we want to describe in order to identify our phenomenon? Well, for example, we are interested in the motion of the stone. Now, we need to select at least one physical observable. What we want to measure, I would like to remind this to everybody, physics is about measuring things. No measure, no physics. I love my theoretician colleagues, but still, of course, and they agree with me, no measure, no nature, no physics. So what do we want to measure? A physical observable, something that you can observe. And well, we pick up the position of the center of mass of the stone. Well, I remind you that the stone, while it moves, if you look, if you observe your phenomena, the stone quite easily will also rotate. It has in principle at least 6 degrees of freedom if it's a rigid body. But we focus only on one, the position of a center of mass. So we reduce that from 6 to 3. And then what we want to observe how this quantity change with time. What happens when the phenomenon goes with time. And what we observe that the motion is parabolic. So the trajectory is a parabola. This observation is not trivial at all. It took some time to come to this point, and it was Galileo Galilei who first discovered that the motion was a parabola. Why Galileo was interested in studying this motion? Because at that time, right, exactly like now, if you want to survive, if you want to do science, you need to find a job. You need to find somebody who's paying your salary. At that time, the salary was paid by the powerful people, and they were not interested in throwing stones. They were interested in using cannons. So the idea, if I have a cannon and I point the cannon in that direction and I fire my cannon, where do the bullet go? Okay. So this is what Galileo was doing, studying the motion of bullets out of cannons. And then we can ask a number of questions. So now we have a parabola. How does the parabola change if we, for example, change the initial velocity or change the angle? And so based on these experiments, we can do what Galileo did. Galileo found the equation of the parabola. So in a parabola, this is a two-dimensional motion. You have y and x. And if you go and look at the trajectory, this is exactly a parabola like this one. Galileo Galilei, discorsi e dimostrazioni matematiche intorno a due nuove scienze attenenti alla meccanica e i movimenti locali. 1638. Now, that's hard to translate because this is old Italian. So it's speeches and mathematical demonstration around two new sciences dealing with mechanics and local movement. Okay. Are we happy with this? Do you want something else? Is everything that we want to know about this phenomenon? Well, we would like to know how X and Y change with time. That's just the trajectory. But how long does it take to go through this trajectory, for example? And how this time depends on the initial speed. So the last point goes beyond Galileo. Galileo was not able to solve this problem. Maybe today we could use some clever algorithm. So machine learning could do that for us. Could find the time equation for X and Y, starting from the data, from the observation. This could, in principle, can be done. Luckily enough, we at that time we didn't have machine learning, so we couldn't use it. But now, if you have the time equation and you ask question, what happens if I change the initial velocity, if I change the condition? Well, I'm not sure that machine learning can give you this answer, but at that time we were lucky because there was this guy, Isaac Newton, which came with the solution of this problem, meaning let's suppose that there is some wind, there is some friction in the air, speed changes, initial angle changes. And so out of the curiosity, of Sir Isaac Newton, we have now the equation of the dynamics. This is way more useful than the equation of the parabola, because this tells whatever is the force F. So if the force it changes, it's not just the gravity, but there is some friction, for example, or the gravity changes, you are in the moon instead of being on Earth. How does it change? Okay, and so this is what Newton gave us. Thank you, Sir Newton. This was an example, just throwing a stone. This is how we make our models. I want to give you just a very simple additional example. Sorry, I think I made a mistake. No. What is it? Okay. Okay. Now, let's look at some more complicated system, a dynamical system, which is not just throwing a stone. Let's look at the case, for example, of a Brownian motion. Brownian motion, you have a small particle. Initially, it was a pollen grain. You put this particle in the water, and the particle moves in a very complicated way. This is very well known since the 1800s and even before. Robert Brown was the guy who did all the observation experiments. And then now you want to build a model for this phenomena. This is a different phenomena for throwing a stone. Not so easy, but nevertheless, as a physicist, we did that. And Albert Einstein was the guy who first found the description of this phenomenon, but I prefer, that was 1905. 1908, 3 years after, Paul Langevin came with a, to me, better explanation, or at least easier explanation. It's the Langevin equation, has been mentioned before by Erik. I'm not going to go into details here, but basically you use the Newton model and you change the force. The force now is not just a deterministic force or constant force, like the gravity, but you introduce a stochastic force, something that changes randomly with time. That was a very brave assumption by Paul Langevin. Okay, just like Paul Langevin, he was known for many things. Among them, he was the lover of Marie Curie. After Pierre Curie's death, Marie Curie established a relationship with Pierre Langevin, and that was not very well seen at the time. People were very strict. Okay, so the beauty of Langevin approach stays in the identification of two distinct forces that they come from the same physical source, which is the water. These forces are the drag, the friction drag, and the heat from the water molecule. I want to give you another example, slightly more in detail, but this is not motion of something, just to explain why physicists are so powerful in making models. For example, the epidemics, something that we had to deal with sadly in the last 2.5 years. This is a model made by two scientists about 100 years ago. Kermack and McKendrick, these were two Scottish scientists, and they came out with this model to explain how an epidemics develop inside a population. And the model is very simple. The population is divided into 3 compartments. So there are the people who are healthy, like hopefully we are here, and they are called susceptibles because they can become infected, but they are not infected. Then there is a group of people who are the infected, okay, the red one, and then they are the removed, so people that overcome the infection or died under the infection, but certainly they do not belong to this. So all the population can be divided into 3 groups. The model is very simple, as you can see. And then they came with the equation on how do this quantity change with time, because we know that change. There is a probability, beta, that from being healthy, you become infected. And then there is another probability that after you are infected, you become removed, meaning you heal, you are healthy again, maybe immunized compared to the virus, or unfortunately you die. So you can write down the equation. These are simple differential equation. The dot means differentiation over time. So you have a set of 3 equations, and you have a condition, of course, that the total number of people is constant. So this is a simple model, okay? It does not take into account the fact that new people are born. So this is it's the easiest model actually that exists for this, but it works pretty well. In fact, if you look at the evolution in time, you see the typical curve of every epidemic. Every epidemic wave has this shape. Okay, and of course, the shape depends on the probability to go from one container to the other, one department to the other, and that's beta. In our model, beta is usually come from 2 factors that we call C. C is the promiscuity. How many people you frequent, how many people you meet, what are your attitude, if you go out a lot or if you stay at home, then C. And then there is T, that depends on the virus. How transmissible is the virus? If the virus is very, very aggressive, as they say, the virus is a small machine. It's a fraction of DNA, has no will, has no personality, is not even alive. It's just a small mechanical machine. Okay, now, of course, you can act on C through the lockdowns. You want to change people's attitude. You forbid the people to meet other people, or you can act on T through protection devices. You have the mask, so the virus has more difficulty to attack. Okay, but if you look at experimental data, these are observational data through the world, you see that there is a lot of fluctuation inside. So we thought that maybe we could use our knowledge on noise to study this model. And so what we did, I'm not going into detail here, we added a fluctuating terms to the description of this coefficient, okay? And that was interesting because there was a long debate in Italy if, say, time-limited event could be important or not for the epidemics. For example, a festival, for example, a concert. Let's suppose that we go to a concert. The concert lasts only for 2 hours, but all the people come together for 2 hours. What it will be the impact of this event on the following days? This is an interesting question, okay? So we try to study this question using stochastic dynamics to simulate and to model this. And it was interesting because it depends on the feature, the time feature of the stochastic noise, meaning what is the correlation time? So what is the quality of the contact that you have? If the contact is just an instant contact, or in contact that comes with some, for example, you go out to dinner, or you shake hand and that's it. So the consequences for the epidemics are associated with this characteristic, with feature, and we showed that depending on the feature of the noise, there will be very much different consequences from this time-limited event. Okay, I want to finish this presentation, just leaving you the last message. The model are not only useful to describe, of course, physics, what exists, but they are time-traveling machine. The models that we make are useful to predict the future, but also to post-predict the past. And just to give you an example, for example, we can say in Florence, next August, the sun will rise at 5:36 and will set at 1854. How do we know it? Well, the talk from Professor Vulpiani yesterday showed us that our model are actually able to predict the motion of the Earth, the sun, and the moon. And that's enough to answer this question. And also, I said, post-dict we know, for example, that in Paris on July 14, 1789, a quite remarkable day, I say, the sun rose at 4:10 and set at 1958. So our model worked in both directions. However, the time is associated with change according to this perspective. This was a notion known since a long time, and it was part of Aristotle's grasp on the topic of motion and time. So let's suppose that we have a particle that sit on a horizontal table. And in classical mechanics, we can describe the evolution in time of this particle. Clearly, how well do we know the position of a particle? We can measure it. But even with the most sophisticated measurement system, like the gravitational wave detectors, we know the particles only with a certain amount of uncertainty. That's the error, measurement error. If the force is 0, the particle will follow this kind of equation. So the uncertainty in the position of the particle eventually will grow with time. But if we start with the velocity that is 0, or small compared to 0, that will go nowhere, okay? So in principle, the particle can stay put in the position where we left. In quantum mechanics, it's slightly different, because in quantum mechanics, still we can describe the time evolution of the position of a particle, but there is a complication. The complication comes from the indetermination principle. So you cannot have at this very same time velocity 0 and position fluctuation 0. So the uncertainty on your velocity and the uncertainty on your position cannot be 0 at the same time. What does it mean? It means that if you put a particle on a table, according to quantum mechanics, the particle will not stay put. If the particle is put, according to Aristotle, time does not exist. No motion, no time. In quantum mechanics, the particle will not stay put. Immobility is forbidden by quantum mechanics. And so time is unavoidable. Time is a necessary feature in quantum mechanics. It's not a necessary feature in classical mechanics. In principle, you can forget about time. Not in quantum mechanics. Time is inherently present into our description of the universe. And there is also another feature, which is interesting. How does the ball move? Our particle, how will move according to quantum mechanics? Well, more or less like this. Well, it's not a trajectory quantum mechanically, but certainly the uncertainty will grow with time and will grow according to fluctuations. So the position will be subjected to a quantum fluctuations. So time, quantum fluctuations. Where do the fluctuations come from? So the analogy between the thermal fluctuation of a Brownian motion and the quantum fluctuation in the position of a particle has attracted attention, of course, in the last 50 years in the physics community. I want to mention these people who have been looking into this problem, the role of quantum fluctuations, and how do they fit into the quantum scheme. And I think this is interesting. So at the basis of this approach, there is the idea that the presence of fluctuations lurks in the most minute structure of space-time. And I think this is something worth thinking about it. Okay, 2 messages to take home. 2, scientific knowledge arises from the world of scientists that build models, meaning struggle to find meaningful questions to be answered via experiments. Second, randomness, noise, fluctuations are essential ingredients in this model, because far from being mere disturbances and approximation, for what we presently know, they belong to the very fabric of the space-time. Okay, so if you want to get more information, these 2 books deal largely with the topic that I mentioned here. Thank you.
Thank you very much, Professor Erik Aurell. And now we have time for a few questions. Yeah, sorry.
Thank you for the very nice talk. Thank you very much. In terms of finding the features in the residual gravitational wave data, the LIGO-Virgo thing, I think there are people like having some particular signal in mind and just trying to data mine the rest of the things. Can you comment on this?
Sure. Of course.
Or did they find anything interesting?
No, that's exactly what should be done. It should be should guess some possible mechanism to generate gravitational wave. For example, tiny black holes. Well, how small can be a black hole? But somebody thinks that there are primordial tiny black holes that survived the evolution, and they can be as small as few microns in diameter. And sometimes the people think that they can be also attracted by large masses, and can one legend, I don't know how good it is because I'm not an expert on that, but there is people that says that there are tiny black holes trapped inside the Earth, for example, and they keep oscillating around the gravitational center of the planet. I don't know if this is true. Maybe, I don't know. So, and these people think that they might emit a weak gravitational signal that can in principle be detected. So there are studies on that. Estimate, maybe they are lacking few orders of magnitude, I don't know. But that's an approach. So you imagine, you figure a possible mechanism, and then you go looking into the data. That's something that the community of science actually require. The gravitational wave detection started more than 100 years ago, but it was plagued by many, many false alarms. People that said, okay, we have observed that. But the community, in order to see this, the community, in order to award the Nobel Prize, they wanted a detection at the same time in two very instruments very far away from each other. That's the two LIGO detector. And now we have three detectors with LIGO and Virgo, and then there will be a fourth detector with Kagra in Japan. So the number of detectors, because that's what you need in order to be sure that this is a real signal, it's not just an artifact.
Yes, there's a question over there.
Thanks for interesting talk. As a layman, I'm just coming into like observational case. So you are talking on the big data. There is a large amount of data, but finding the solution is in the timeous manner is most important as well. If I have a problem, I need to find a solution immediate, in terms of the time. So in that concept, I'm thinking that the probability of distribution and the filtering of the data is most important. Can you comment on that?
Well, that hits the topic of data analysis, of course, and this is a topic that has been around for many, many years. It is the very basic of statistics. Look, I'm sober about machine learning. I'm not against this technique. Besides, I've been teaching computer science for some time. And my idea is the following. Machine learning presently are very, very powerful technique, but it's a technique among others that has been developed on the shoulder of giants who studied the statistical data analysis. It's not the end of it. We have not seen the end of it. The question could be, there will be machines able to figure out the model, the physical model. Machines able to do what Galileo did, or machines able to do what Newton did. There will be, not now, not these machines. We need way more. Why am I sure that there will be machine like that in real artificial intelligence? Because we are these machines. We are machines. We have been built, and now we are going to build other machines. By the moment that we can do that, other machine eventually will be able to do that. That's my point.
Okay, I think this is a very good point to stop if there are no more urgent questions. Thank you very much for this talk. And the promise that it changes your life if you take it serious, if you read the books and you think about it. Okay, and we need you to think about it so that we can make progress. Thank you very much. I also want to thank you on behalf of the School of Physics and of course the College of Agriculture, Science and Engineering.
Thank you so much.
Yeah, thank you for coming and sharing your wisdom with us. And I hope you come back and we can further interact.
Hopefully.
Thank you.
Thank you.
Okay, this brings us to the end of the morning session. Today is also at the same time the end of the Nobel Symposium, at least as far as the talks are concerned. And I want to thank all the attendees that they came and contributed with their questions and with their presence. And I would hope that we can do this in a regular, in a more regular fashion, so that we have often such discussions, because this is, in my opinion, what we need as a university. And thank you again for coming, and see you next time. Thank you. Let's give the word to Professor Amar, who organized the symposium for the last round. Thank you.
Yeah. Thank you. I just want to say thank you very much for you guys to come to join us for this very exciting Nobel Symposium outreach program. And just one correction: tomorrow afternoon there will be a final outreach talk at the University of Witwatersrand in the afternoon. There is online. You certainly don't need to fly to Johannesburg. There's online connection that showing the poster. And but regarding the KZN outreach program, we have yesterday afternoon, we have yesterday evening, and today this morning, and it has been very successful, I believe. And thank you very much. And in the meantime, I would also thank our partner, the National Institute for Theoretical and Computational Science, chaired by my friend Professor Francesco Pocciconi, and also enormous support from the STIA, the Stellenbosch Institute for Advanced Study. So let's go give all our partner a big applause.